having estimated the realignment parameters, that is to say the amount of motion that's in your time series, the next step is to try to deal with it through realigning the data. And that's what this video is going to discuss. So, as I say, once you've estimated these motion parameters, what you then need to do is correct your image in some sense, right? So, for instance, if I had an image here, just again, a very simple little square image where I've simply coded the values of these colors in numbers to make life a little bit easier. And let's just say it had a whole voxel translation in X. I'm literally going to move it to the right by a whole voxel, which, as I said in the last one, would be too much motion, right? I wouldn't do this typically, but for illustration purposes, what you'd get is something like this. So the left side, the 741, has now moved over a whole voxel, as have all of its neighbors, and you've lost your 339, the right side of that image, right? It's no longer there because it's been moved out of the field of view of your image. But because you didn't have anything to the left of your 741, all you can do is put in zeros there because you didn't have data. You didn't collect those data that would be needed. Because the person literally moved partially out of your field of view and then partially, back into it, by not collecting the data, you just fill them with zeros. And this really illustrates both the process, but also one of the main consequences of the process, which are known as edge effects. So by moving this image, one voxel translation in X, I've introduced a strong edge effect on that left side where all of a sudden I've filled it with zeros, lack of any data whatsoever. But there isn't anything I can do. If we didn't collect the data, we don't have anything to put there, which is why, a translation of a whole voxel is too much, right? It introduces this massive artifact in your data. In practical terms, we're always talking about movement that's less than a voxel. So I'm just going to illustrate the same thing with only a half voxel translation to the right in this case, right? And one of the consequences of this is that you now just have to sort of average the two voxels. So the 7 and 8, which have moved half a voxel over, now become a 7.5. Similarly, the 8 and the 7 have become a 7.5, and the 7 and 3 have become a 5, because I've added them together and divided by 2. But what you can see is you still have this edge effect on the left side here, where the first voxel's value is 3.5, because I've averaged 0, which is data that I didn't collect, with the data that I have, the 7. And nonetheless, I get this kind of darker edge on the left that is an edge effect due to the realignment. Realignment always produces edge effects. It's not just on the edges of the field of view, but also on the edges between tissue types. So for instance, earlier I showed you a person who was moving a lot, and we looked at a voxel that was in their cerebral spinal fluid, which gives you really bright values, that had moved into gray matter, which gives you darker values. And you get the same kind of edge effects there, right? If you're mixing cerebral spinal fluid and gray matter, then of course you're comparing apples and oranges and you're getting these intermediate values that are neither one nor the other. So you get these edge effects as a result of realignment all the time. And this is an artifact that we need to be aware of. Informally, I had suggested that all you can do is, you could just average the two numbers to figure out what the value would be. And if you were halfway in between them, then that's fine, right? But this is an example of what's called a linear interpolation. So if these are the data values that I've recorded at one particular voxel, and I simply drew little line segments between them so that there's a straight line, then no matter which, how far I'm moving, if I'm moving halfway, then it's just I add the two together and divide by 2. But if I'm moving 7/10 of a step in one direction, then it's a slightly different, it's not add it together and divide by 2. You actually have to weight it by how far you've moved. But that's what a linear interpolation does, right? It allows you to sort of say, well, if I just draw a dot at the point where I wish I had collected the data, what would the value there be? And I'm going to replace it with that value. That is a quick and dirty version of linear interpolation. It's not the optimal way to do things, though, because, well, for a variety of reasons. So one of the things that people often do is something called spline interpolation. That is to say, they want to make sure that the movement curve doesn't just have these little angles in it at each point. It's smooth. And to do that, you can use, rather than using line equations, you use curve equations. So you typically use like a third degree spline would be something with an x squared or x cubed factor in it, excuse me. But you can do more complicated splines if you want. The point here is, I'm not asking you to understand the math or go into it. If you're interested, by all means, it's not particularly complicated, and it's very common in basic numerical methods approaches. But it's a way of producing an interpolation. That is to say, if I want the data point in between the places that I actually collected it, then I need to estimate what that would be. That estimation is known as interpolation. And spline interpolation is slightly better than linear interpolation for a variety of reasons, basically around the idea that probably head motion was smooth. It isn't the case that somebody was moving in a sort of robotic way. They were probably moving in a much more smooth fashion. So it's a better estimate of what people are actually doing. And again, same thing. You can interpolate by figuring out where you wanted to collect the data, go up to that point on the curve and take that value and replace it with what's in your image. There's an even more sophisticated way that's known as sync interpolation, which uses a much more sophisticated convolution kernel, which is what I'm showing here. But basically, it's a weighted average of the things around it in this case in one dimension, but you can do it in 2 or 3 dimensions as well. And it has the advantage that it gives you a smoother function, but it also isn't as locally dependent. So that is to say, it's less sensitive to local sources of noise, which is a really important process. The downside of using it is it's computationally more expensive. So back in the late 90s and things, people mostly didn't use sync interpolation because the computers just weren't fast enough to do it in a reasonable amount of time. Nowadays, that's not an issue at all. On the other hand, sometimes for things like realignment, people still don't bother to use sync interpolation just because the advantages relative to linear interpolation or even spline interpolation are relatively small with realignment. It'll come into its own a little bit more when we talk about normalization in next week's set of lectures. So one of the things that's important here is that we're doing this process to try to get rid of this source of variability in our data that's due to the fact that people are moving their head, right? And almost always people refer to this as motion correction. In multiple times, I've talked about correcting for some of this motion. But I don't like the term motion correction because it implies that it undoes all of the effects of motion. It does not. It simply realigns the data. And I've given you an example of that already with edge effects, right? Somebody moved their head from one spot to another spot, and as a result, I have to take in some data from outside of my field of view. Well, I can't correct for that. I didn't collect the data. There's no way I can make up what those data could have been had I collected them, right? There's just nothing that can be done in that case. And those are edge effects. So realignment doesn't correct for edge effects, but it doesn't correct for lots of things. It doesn't affect what are called partial volume effects. It doesn't correct for within volume motion effects. And to make things a little bit more complicated, there are distortion effects that affect where you are in the magnetic field. So that is to say, I suggested to begin with that a rigid body transformation is a totally sensible thing to do because the shape of your brain isn't changing as you move it around in a scanner. That's true. The shape of your brain isn't changing, but the shape of the image that you're collecting is changing a little bit due to distortion effects. And go through that. Okay. The key here is that some of the residual motion effects, some of the artifacts that are due to this residual non-corrected for parts in realignment can be an order of magnitude or more larger than bold signal effects. And as a result, you can get these whopping great big signals in places that are not realistic due to residual motion artifact. So let's talk a little bit about partial volume effects, because when we talk about a voxel, I've kind of implicitly assumed that that voxel is measuring one thing, and that that's a sensible thing to do. I've talked about it as measuring cerebral spinal fluid or measuring gray matter, but that's just never the case, right? It's always a combination of multiple tissues. So I'm just going to try to zoom in here on a part of the brain, then look at a particular voxel. And then when we look at this voxel in a little bit more detail, you can see that there is gray matter in it in terms of the sort of purple edges. There's white matter in terms of the deeper structure underneath the gyral crest. But then there's also cerebral spinal fluid and blood vessels in the sulci that's included in this voxel. So you've got all three of those in different proportions in the voxel. Four of them in this case. And you can even look at it in more detail than that. You could say, well, you say gray matter, but what about dealing with the different layers of the isocortex? I mean, how much layers of 2, 3, and 4 are we getting versus 5 and 6, etc. So the source of the signal that we're measuring in any given voxel is always a combination of different types of material. The one potential exception to that is if you happen to have a subject with big ventricles and you happen to be in the middle of like a lateral ventricle, you might be getting essentially cerebral spinal fluid. But that's not the stuff you're interested in because it's not generating bold signal. Anytime you're looking at bold signal, it's being generated by a complicated combination of multiple tissue types. And what that means is even small amounts of motion, a millimeter, maybe even less, change the particular proportion of the material that are generating the signal. So by simply shifting this, like rotating it a little bit in one direction, you could, for instance, increase the amount of white matter, decrease the amount of gray matter, and perhaps you don't affect cerebral spinal fluid and blood vessels in this particular case. But the key is, because you're measuring from literally different cells that are giving rise to the bold signal, you are not dealing with this when you do realignment, right? That you've changed the source, and there's no way to know exactly what was the source to begin with because we just don't have this kind of resolution. But it's a residual effect of head motion, and there's nothing we can do about it in terms of realignment. The other thing that we should think about is, what about really quick motion, right? There are lots of things that are happening in less than 3 seconds. So I've talked about it in terms of one TR to the next TR, which is 2 to 3 seconds. But what about the things that are happening in under 2 seconds, right? So if your head's at one position and it moves really quick and comes right back so that it's there 2 seconds later, then as far as the scanner is concerned, it didn't see any effective motion, right? However, you've moved. And there are some big sources of physiological sources of these effects. One of which is your heartbeat. It's beating away at whatever your resting heart rate is, or perhaps you're in the scanner and a little bit anxious and therefore it's beating a little bit faster. But of course, every time your heart contracts and sends a high pressure wave through your arteries, it causes a little bit of motion in your head. And it depends where in your head, how much motion it is. So like along the brainstem where the basilar arteries are strong and receiving very direct high pressure blood from the heart, you actually get quite a bit of movement. Whereas on the outer edges of the neocortex, you get less. This is all things that are not being corrected, by realignment. It's affecting the realignment, but it's doing it at such a rate that we don't have enough data, again, to sort of tell you how to deal with it. One of the approaches that some groups and some companies have used is to try to correct for motion at the time of acquiring the data. So everything I've told you up till now is we acquire the data, we look at it, and then we try to deal with it through a realignment process. But what if we sort of turn that on its head and said, look, while we're collecting the data, we try to estimate how much a person's moved from slice to slice, so like every 60 or 80 milliseconds. And based on that, if we can estimate that correctly, we can adjust the gradient coils to act like the head was in this new position relative to the old position. And in theory, that's a really good way to do it, because if you're accurate, then all of these effects that I've talked about that aren't corrected go away, because now you're changing where you collect the data from. So you're collecting from the same tissue. You're not getting these kind of edge effects due to field of view, because you've literally changed your field of view to correctly reflect where the head is. And of course, all of the motion that comes from heart rate and breathing and things like that is also corrected for, because it's happening at the same sort of speed as these corrections to the gradient coils. So in many ways, this is a sort of an optimal way to do things. And it does work extremely well for small gradual motion between volumes, right? Because the key is, if you estimate this correctly, if you estimate it wrong, you're going to enhance the effects of motion. And small movements of the head that are smooth and continuous are easy to estimate. When something goes a little bit more wrong, somebody coughs or sneezes or does some sort of bigger movement, then the estimation procedure fails, because to do it rapidly and successfully, you make certain assumptions about things being smooth and small. And as a result, you then collect the wrong data because you estimated a movement that didn't happen. You change the gradient coils as if it did happen, and then treat it as if it had happened. So it's a really error-prone thing that it works really well for good participants, and it works very, very poorly for what you might consider bad participants, movement-related participants. So in some ways, it can be very useful for difficult to scan populations, right? So if you have neurological patients or some other kind of patients that you're testing who are cooperative, but they're hard to get, then this is really good, because man, is it painful to realize that one of the 12 patients that you were able to recruit, you have to throw their data out because they moved more than 3 millimeters over one of the runs. Similarly, this is sometimes helpful with children, particularly if they're fairly cooperative and you're good at keeping them engaged attentionally, because again, they can be hard to bring in. You can only do it during, not during school terms and all the rest of it. So it's a technique that can be very useful. I tend not to use it because I tend to scan normal, healthy adults, and they're just very cooperative. And moreover, if they're a big mover, I can just throw their data out and replace it with some other volunteer. Not a problem. The issue is that the data look great in terms of their head motion when you get it off the scanner, because that's what this corrected for. But it doesn't really give you any information about how much it thinks they moved. So if it thinks they moved very small amounts, the data look great. If it thinks they moved very large amounts, the data look great. And you have no way to tell that from the data that you have. And the problem is there's a big difference in terms of the data quality in those two conditions, and you have no information about which is good and which is bad. So I avoid using prospective motion correction, but there are certainly scenarios where it's a sensible thing to do. And, it depends a little bit on the question and the population that you're testing. In some scenarios, you can also get the scanner's idea of how much movement it's trying to correct for. And when you can get that, then at least it does give you some information about whether or not it thinks these are good or bad data, and you can take them appropriately when you do your analyses.